describe a recent paper on trying to describe ADS 5 times S5 at small radius using topological A-model. So let me start by saying some things about pure spinor formalism with ADS, which in some sense the ADS formalism is simpler than in a flat background, but in a kind of a unusual way. So first of all, the ADS action, so pure spinors, you start with theta lefts and theta rights. So type 2b, they have the same chirality. In a flat background, they have also conjugate momentum, which I'll call p right and p left. And then, of course, you have the x's, and you have the pure spinors, which are also first-order actions. So they also have. Okay, so of course the central charge is 0 because you have as many bosons as you have fermions. Everything's conform weight 0. Now, one thing that happens in a flat background is that the Lagrangian, if you do a space-type supersymmetry transformation, it's not invariant. It changes by a total derivative. So that's like in the Green-Schwarz action. It turns out the ADS 5 times S5 action, all the PSH24 is manifest. So the way you do that, so that was first done by so of course they're no longer going to be left and right moving. Let me call them theta and theta hat. So as in Metsayev-Zeitlin, you combine the variables into a coset of this type. And then you form currents. So currents are J, let me call it J. A. So this takes values in the adjoint of PSU224. And of course, you also have J bar. And these are manifestly PSU24 invariant, just because G multiplies the PSU24 transformation is just multiplication on the left by a constant matrix. So these are all PSU24 invariant. And then the Lagrangian is just then there's some terms for the ghosts. So these are the pure spinor ghosts. You have some terms of this type. Then you also have a so the coefficients here are different than in Green-Schwarz, but otherwise it's very similar. So something like 3/4 and 1/4. So I'm not going to be. So of course, Lagrangian is constructed so that it's BRST invariant, where the BRST operator is. I didn't tell you. So you can contract alpha and alpha hat using gamma 5 matrix. So this is also something special in ADS 5 times S5, is that you can contract these two indices using 8 alpha alpha hat is equal to gamma 0, 1, 2, 3, 4. So it's just a 5 form. And what you find is that the flat space action, this action, of course, doesn't depend on the conjugate momentum to thetas, because essentially when you turn on the Ramon-Ramon background, you can integrate them out, because the Ramon background is quadratic in P left and P right. So that's why this action, you can see G only depends on X theta and theta hat, because I've integrated out the P and P hat.
Could you remind me why the coefficient 3/4 and 1/4 are different from the Green-Schwarz?
So in Green-Schwarz, of course, you have kappa symmetry, and it turns out this is anti-symmetric in alpha and alpha hat in Green-Schwarz. So it's just they have opposite signs. In pure spinor formalism, BRST symmetry implies that you have another term, which is of course necessary because you don't want kappa symmetry. And the different coefficients here are required because when you integrate out the P and P hat, that essentially gives you something which is symmetric in alpha and alpha hat. So the symmetric term, of course, in Green-Schwarz, you don't have these P and P hats. So that's why it's different from the Green-Schwarz term, and that's why it's not kappa symmetric, but it is BRST invariant. Okay, so the BRST transformation is also, so whenever you see an alpha and alpha hat, okay, sometimes I'll forget to go. And of course you also have the right moving one, which is lambda bar. So these turn out to be holomorphic and anti-holomorphic in this background. And another thing which is slightly different than a flat background is you can formally, so in a flat background for people that know the pure spinor formalism, to construct the B ghost you have to introduce a new non-minimal variable, which is also called lambda hat. So it turns out that in a flat background, so you have lambda left and lambda left hat, and lambda right hat. And the B ghost is something like, in a flat background, you need lambda hat to write the B ghost. So it's something like lambda hat times, there's a term, something like dx slash d. And then there's other terms. So this, now in order to write the B ghost, you have to divide by lambda. And it turns out that these inverse powers of lambdas, you have to have terms with up to 4 inverse powers of lambdas. And these give complications in multi-loop amplitudes, et cetera. But at least for up to 2 loop amplitudes, you can compute using these, and everything works out fine. Now, in pure spinor, in ADS background, as I mentioned, it's possible to contract lambda left with lambda right. So if you want, you can consider this object, where this is the same as this. Okay, so instead of course, the D gets turned into a J. So this now becomes something like JA gamma A alpha alpha hat J alpha hat. So this object is, of course, not holomorphic, because this lambda right is not holomorphic. But it turns out you can show that Q with B gives you T. So here, of course, you divide by lambda left, lambda right. And you can show that D bar of B is actually Q of something. So in some sense, you have this n equals 2 structure, which is in some sense is simpler than in flat background, because you don't have to introduce both a non-minimal lambda and a right-moving lambda, but it's a little bit strange, okay? So it's not, okay, so these are the features of the ADS 5 times S5 formalism with pure spinors. And as I mentioned, the nice feature is that PS224 is manifest, and that you have this n equals 2 structure.
Is there any issue with having arbitrary inverse power of lambda lambda bar here?
Again, nobody's done computations with this, so I don't know how to answer that question. So there might be. So it turns out that lambda lambda bar also has some special meaning, which is that the Lagrangian operator is, of course, dimension 1, 1. And you can ask, what's the dimension 0, 0 object, which is related to this by the usual descent relations? It turns out that the 0, 0 operator, which is related to this, is just lambda left, lambda right. So it has a special role in the theory, but I can't answer the question about if this is actually something consistent or if it's going to cause a problem. Okay, but in any case, there's one other thing which is nice, which you can do. So, so if you ask how the thetas transform under this BRST and the B ghost, then you'll find that the thetas, the superfield that you get, let me write it like this. It starts with theta, and then you get a term which is lambda. And the other term you get is W bar, let me call it kappa bar plus. And then you get a kappa plus kappa. This could be some auxiliary field. So what I'm constructing now is a superfield, which depends on, of course, z and z bar, but also on its chiral. So it only depends on kappa plus and kappa bar plus. And similarly, you have theta bar, which is going to be antichiral. So we'll start with theta. And this would start with this is some auxiliary field again. So all I'm doing is I'm using these n equals 2 generators and seeing how they act on the thetas. And they seem to fill out this chiral and antichiral superfields. So I can ask, can you write this Lagrangian in terms of these thetas? Oh, there's something I forgot to mention. So lambda is a pure spinner. Right? So lambda satisfies lambda gamma. That's both in a flat background and in ADS. Okay? So it has 11 independent complex components. Now, another thing you can do in ADS is, of course, you have the x variables, which, of course, describe ADS5 and S5. So this is SO42 over SO41, and this is SO6 over SO5. So the pure spinners, if you do an SO41 times SO5 transformation, in other words, if you do a transformation which is in the coset here, they stay a pure spinner. But if you start with a spinner which is pure and you do a SO42 transformation, it's no longer a pure spinner. So in other words, this lambda is, of course, I can decompose it 10 dimensions. Of course, it's a representation of SO91. I can also think of it as a representation of SO41 times SO5. Right, so then it has two kinds of indices, so I'll call them, I don't know, A and let's call them J. So A would be a four-component, I think of this as a four-component spinner of SO41 and as a four-component spinner of SO5. Now I can extend these to be four-component spinners of SO42 and SO6. But then if I do an SO42 times SO6 transformation, which is not in this, it will no longer stay pure. So when I wrote down lambda here, probably I shouldn't call it lambda because that's going to be confusing. Let me call it Z. And this is Z bar. These will be the conjugates. Y. So theta and theta hat are, of course, 16-component spinners. So these, of course, also have to be 16 components. So these Z's contain information both about the X's and the lambdas. So the idea is that you can, if X is 0, so if you choose some point in X which you think of some special point of ADS5 and S5, then Z is going to be a pure spinner. But as you move away from that point, Z is no longer going to be a pure spinner. So Z encodes both the position on ADS5 times S5 and the pure spinner. So of course, together they should have the same number of degrees of freedom. And of course, that's true because you have 5 plus 5 degrees of freedom here, and 11 plus 11 here, the left and right movers. So together you get 16 plus 16. So that's another thing about ADS5 times S5, which you can't do in flat space. So the idea is that these X's and lambdas are naturally combined into these 16 component things, which of course you get by hitting Q and B on theta. So they will generate not just a pure spinner, but it also will generate the X dependence here. Okay, so that's, these are the kind of superfields which you could try to write an n equals 2 action out of. So the natural thing to do, so these, it's natural to also write them in terms of these so now it's going to be SO42 or SU4, or SU22, I guess, times SU4 notation. So this would have two kinds of indices. So this will be a 16-component object. And you can, you can write an action of this type, which was done together with Kumran, Rafa. So you have an n equals 2 action. So this is supposed to be trace, I mean, this is a 4 by 4, etc. This is AB. This would be BJ. So theta would have an up SU22 and down SU4, and theta bar would be the opposite. So you can write this kind of linear sigma model action. And if you put in a phi Heliopolis term, which would be something like R squared V, this is essentially the same action as writing G minus 1 dg, G minus 1 d bar G. The supersymmetric completion of this, where G is, instead of being in PSU224 over SO4 1 times SO5, it's this coset. So this is just this is a purely fermionic coset because I've divided out by all the bosonic elements. And you can think of the lowest component, or the fermionic components of these G's as just being these thetas. So it has 32 fermions, which are just the components of G, which sit in the off-diagonal components. So this would be theta, this would be theta bar. And this action is just a supersymmetrization of this. So, of course, it's a different action from the original ADS5 times S5 action, but at least we conjectured that it was related. Okay, so, I mean, the idea was that you can now take the limit R goes to 0 and try to understand this theory.
Sorry, just to understand the relation. Is it supposed to be RG flow?
So this is supposed to be conformally invariant.
Oh, it is?
Yeah, so, this supercoset, you start with PSU24, and this is a symmetric space. This is going to be conformally invariant, this action.
Wait, but I thought you started with a gauge linear sigma model. That one.
With the V, is that what you're saying?
Yeah.
So I can integrate out V, and you land on this.
This integrating out procedure. Wait, is there a
So
term for V? Oh,
no.
You're already at the.
Right, so the auxiliary equation of motion for V is just R squared is equal to phi theta e to the V theta bar. So if R is 0, then something different happens, but suppose R is non-zero. Then this tells you that you can choose a gauge in which one of the components of theta is 1, and then you get this coset.
Okay, it's like the usual gauge linear sigma model, you have a kinetic term, but you have already set that term to 0.
Right. Right. Okay, so so we weren't able to get very far with this, but then there were some papers by Gopal and Gabardiel where they showed how to construct the vertex operators for free super Yang-Mills in terms of these twistor-like variables. So the twistor variables, let me call them phi. So they take, instead of, so let's say sigma ranges over all the PSU24 fundamental representation indices. So they can either be alpha, alpha dot. I'm now, instead of, J before went from 1 to 4. I'm used to using J goes from 1 to 2. So alpha, alpha dot is 1 to 2, and also J and J bar. So this has 4, if you like, indices from the SU22 and 4 indices from the SU4. And these naturally split up into PSU112 squared, which will be alpha J, so I'll call this I and I bar B alpha dot. So these PSU 112 indices are the one. So this PSU 112 times PSU 112, that's a subgroup of PSU 24 that leaves, for example, one of the scalars, a complex scalar invariant of the half PPS state. So, for example, if you consider this super Yang-Mills state where these z's are all in the same direction, that's left invariant by this PSU 112 times PSU 112. So what they showed is that you could construct the vertex operators for this state. So let's say we have n of these. And now in the free case, they don't have to all be in the same direction. So let's call it Z1, Z2. So let's say we have n of these. Then you construct these with vertex operators where each of the phi's have n modes. So you have, one. So essentially at each vertex operator, so the vertex operator for this state, so this is a super Yang-Mills state, which could be half PPS, but doesn't have to be half PPS. So it just has n different super Yang-Mills fields here. And the idea is that if you want to construct the vertex operator for the closed string state that's dual to this, the vertex operator will be built out of modes of these phi's and phi bars.
So that n equals 4 guy only has scalars, or does it also have
No. So you can get, you can get any super Yang-Mills field. So yeah. So these phi's, of course, both have the fermions and the bosons, and by exciting with the fermions and bosons. So the construction, of course, is only PSU 112 times PSU 112 invariant, but you can get all of the, not just the half PPS, but all the super Yang-Mills states in the free case using this language.
Sorry, but they have to be in general protected if you turn on lambda, or?
Right. So we're just doing free. So everything for the rest of the talk will just be free, except maybe the last 2 minutes.
But otherwise, you wouldn't expect them to be supergravity.
Right. So
Some dual to some string states.
that's right. Okay. So they tried to write down a string theory that gave this thing, but I don't think they had some guesses, but I don't think any of those guesses went through all the way. Okay. So the idea now is to construct something which combines these two approaches. So instead of starting with this coset, I'm not going to start with a different. So I'm going to divide by SU12. So what that does is it essentially, instead of modding out this and this, now you mod out almost everything. You're just left with essentially one. You're just left with the states in the upper row and this leftmost column. So the action I'm going to consider is essentially the same as before. But you just have a single, I won't call it theta because it's not necessarily fermionic. Let me call it phi. So now V is just a U1. In this case, it was a U4 V. So this is actually very similar to the action that Witten proposed for the twistor string, but he had a type 2B model. Here it's going to be type 2A. So
Could you say again, what is the difference between this capital phi and the capital theta on the left?
So theta came, if you took the coset and you divide it out by the bosonic elements. Here, instead of modding out by the bosonic elements, I'm going to mod out by this supergroup here. So these components here are essentially, it's always the same G, it's just you're dividing out by a different coset. So the phi's are half bosonic and half fermionic. The ones here the ones here are bosonic. So these are like bosonic twistor variables. So it's something like, I used lambda already, but
Depends on the index.
yeah, that's right. So sigma, if sigma was alpha and alpha dot, it would be bosonic. If it's J and J bar, it's fermionic. Okay, so I didn't mention this before, but this is an A model. Obviously, to have this phi Heliopolis term, it should be an A model. But you can also see that just from the structure of Q and Q bar, that the Q and Q bar are the ones that are twisted. Okay, so the idea is that because it's an A model, these variables here are going to come from holomorphic instanton solutions for this phi. So the equation that you're going to try to satisfy is del bar phi and del phi bar. And now there's one other, we're going to do it r equals 0. So at r equals 0, if you vary v, then you get the equation of motion phi sigma phi bar sigma equals 0. So what this means is that you can, one solution of this is, so solution is phi I bar is equal to x I bar j phi j, and phi bar I is equal to x I j bar, where x is now a supermatrix, so it's a 8 by 8 supermatrix, where the elements here are x alpha dot alpha, y j bar j, and here you have some thetas, theta alpha dot j, theta bar j bar alpha. So this is what's called harmonic superspace, or PSU4 harmonic superspace. So the general solution is obtained by relating phi and phi bar in this way. So if I choose capital X equals 0, I'm essentially left with just these variables. Just the, so if X equals 0, then you just have phi I with an upper I and phi bar I bar with a lower I bar. Okay. So this notation is useful for another reason, which is that W, you can construct superfields which are related to these superspace coordinates, which describe the Super-Yang-Mills on-shell fields. So the relation is essentially the lowest, of course, this is only PSU112 squared manifest. And the way this describes the fields is, if I think of Z as being my 6 scalar, I have too many things called Z, but okay, you'll remember. So these are the scalars. So if I split my 6 scalars into a 1, a 4, and a 1 bar, then the way it works is you get, this is a function of x, and you have y, j bar j, then you have y squared. Y squared is just the obvious contraction of these indices. This is z minus x. And then the fermionic components, which depend on the theta, of course, give you the gluinos. So this is the superfield, which has the nice property that if you compute the propagator between two of them, so let's call this x1 and x2, The propagator is just the inverse superdeterminant of the difference of the supermatrices. So you can show that this is equal to y1 minus y2 squared. So it's equal to, right. Well, the dot, dot, dot depends on the thetas. So, so this will be useful when we're going to use this model to show that you get the right free super Yang-Mills amplitudes. Okay? These are just the propagators for the super Yang-Mills amplitude. Okay, I think I have 10 minutes, is that right? Okay, so
Sorry, just to understand that, is there a priori kind of understanding of the equivalence between this and the original?
good, okay. So there's a hand-waving argument. The hand-waving argument is that all of these cosets, even this one, can be understood as coming from some G over G model. So the G over G model is something where you have G minus 1 dg, G minus 1 d bar G, or this is, sorry, del, where I gauge not just the SO41 times SO5, but the full PSU224. So naively, this is trivial. Okay? But suppose instead of gauge fixing all of the PSU24, I gauge fix different subgroups. So for example, you can think of these variables here as coming from the Fader-Popov ghosts coming from the gauge fixing. So, so this one is simpler than that one. So let's do this one first. So if you, instead of gauging, so of course you have a PSU24 gauge symmetry. And we're going to use the PSU24 gauge symmetry on SO42 times SO6 subgroup of it. Sorry, the other way around. The fermionic, so it has 32 fermionic gauge symmetries. I'm going to use those gauge symmetries instead to gauge the gauge field to 0. Gauging the gauge field to 0 gives me Fader-Popov ghosts, which are going to be these 32 Fader-Popov ghosts. The bosonic gauge symmetries I'm going to use to gauge fix the components of G, which is how I get to this coset. So I claim that this coset you can get by starting with this and doing a gauge fixing. And similarly this one. To get to this one is more complicated. Maybe I can tell you after.
Is there a PRC symmetry of this model?
This one? Yeah, so it's just the usual twisted n equals 2.
Oh.
So this is going to be an A model.
But so you understand the actual map between the field or vertex operators between that and
Not in a direct way. I mean, there's some, it does look related, but I mean, at the moment, I'm just trying to get the right answer, and then we'll see how it can relate to the A disk term this one. Okay.
So here you have a twisted n equal to,
Yeah.
it's
So-
the same structure as related with other.
So again, because the B is funny, it's not, I mean, it's not the usual n equals 2. But here, of course, you have the usual n equals 2. The n equals 2 is manifest. Okay, so what's the idea? So the idea is the gauge field, in order to get the right instanton solution, so of course, if I don't turn on the gauge field, then this just has constant solutions, and you're essentially, there's nothing, you don't get anything. But if you can turn on the gauge field, and the idea is your vertex operators, so the vertex operator that you want to use to describe this state here is going to be described by a vertex operator. I'm going to use the boundary state language, in which the number of edges of the boundary state will be related to n. So this would have n edges. And in order to get this object, you're going to turn on a flux. So the U1 flux going through this, this boundary state should be equal to n. Actually, it's n over 2. But. So what you find is that, obviously, so we'll just do the free case for now. So the free case, the idea is for each vertex operator, you construct this boundary state, which has n edges. The edges all have equal length. And the Riemann surface is obtained just by gluing the boundary states together. So that's supposed to describe the Feynman diagram related to the correlation function of these vertex operators.
Sorry, could you explain what this picture represents? I'm not getting it.
This one?
Yeah.
Okay. So this is going to be a closed string vertex operator. So the closed string vertex operator, of course, is just some operator. But if I use the boundary state language, then the boundary state language is that it's going to be described by some object where I have boundary conditions at the different edges.
Sorry, where does this picture come from?
Okay, so I'm just trying to, I didn't tell you where it comes from yet. I'm just trying to describe what you need in order to describe the states. So I'm going to describe my states by a vertex operator which has U1 flux. So the U1 flux essentially is concentrated just at the vertex operator. And the claim is that, the state that it produces is a state which has these modes. So by turning on the flux, I'm going to get non-trivial solutions to this equation. And the modes coming from each of the vertex operators are essentially going to be these phi's here. And now how the vertex operator, so this is essentially the description in the stuff that Gopal Kumar and people like that work on. So the idea is that the Riemann surface, at least for the free case, is obtained just by gluing together these faces. So of course the idea is that, that the faces that you glue together to get the Riemann surface, each face describes a vertex operator. And then the edges here, okay, so okay, so I'm running out of time, but let's say you want to describe, for example, a cube that's describing, this is maybe too complicated. So, but this is I guess, 6 faces, so 6 vertex operators. Each vertex operator would be describing the straight trace of some Z1, Z4. And then the idea is that the computation you want to do is computation we have, so let me call this 1. So of course there's 6 of these, so this goes from 1 to 6. So suppose you want to do this Super-Yang-Mills correlation function. The way you do this correlation function is this would have 6 vertex operators, so you stick 6 vertex operators on the Riemann surface, and then you just do the tree amplitude of that computation.
Can you give more details how the Riemann surface encodes the information about the...
Okay, so the number of faces is clear, right? The number of faces is just the number of vertex operators. The number of edges just comes by just counting how many Yang-Mills states you have on each face. And then you're supposed to glue those edges together in all possible ways. And that's what gives you the correlation function. And of course, if you glue them together and get the genus 0 surface, then it's genus 0. If you glue them together and get genus 1, then it's genus 1.
These are the weak contractions, basically.
Right. Right. So each Wick contraction is supposed to give you this superdeterminant. Okay, so now the claim is that if you put on this flux, if you turn on this flux at each of these vertex operators, that's going to give you these different modes. And then the claim is that what you're supposed to do is, of course, you're supposed to integrate over all the instanton, all the instanton modes. So it's a topological amplitude, so the only contribution to the correlation function comes from the integral over the modes of the instantons. And then the modes of the instantons, it turns out, okay, so now we have to, the only thing I didn't tell you is how to get, of course, I told you that the number of Yang-Mills fields is n, but I didn't tell you which Yang-Mills fields. So to get the correct vertex operator, you have to stick in this factor of e to the phi x1, phi bar, e to the phi x2 phi bar. So this, of course, is describing n Yang-Mills states. So each of these states here has an x associated with it. So in general, what we're going to describe is not just z, but w, where w is this w here. So w, of course, depends on x. So for each of these w's, you have an x associated with it. And doing the integral over these phi's, because so what you're going to get, for example, for this cube, for example, you'll have a phi associated with this side of the edge, another phi associated with that side of the edge, which I'll call phi 1 and phi 2. Sorry, I didn't say that correctly. I have an x associated with this side of the edge and x associated with this side of the edge. And I have a this dependence on the value of phi and phi bar at the midpoint of this edge. And when I integrate over the phi bar here, I just get precisely the superdeterminant that I want. So the idea is that these propagators here come from integration over these phi bar instanton modes. Okay, so that's the picture. So, of course, this is just a free case. If this, I mean, I think I understand how to get the right answer. Of course, the connection to the original ADS 5 times S5 is still a little bit hazy. But at least it gives you a picture of how to get the correct correlation functions from this description in terms of these PSU112 variables. Now, of course, the challenging thing is to now introduce the R squared. So if you introduce the R squared, what it should do is it should allow you not just to have faces representing the different vertex operators, but also faces which describe the super Yang-Mills vertex. So the super Yang-Mills vertex I can think of as just, it's the cubic term in the Yang-Mills action. So the cubic term in the Yang-Mills action would be things like z times psi bar. These psi's would be the gluino. These would be the scalars. You'd also get things like cubic terms in the gauge fields, etc. So this would be described by some cubic face. So some object with 3 edges. And now the idea is that to get the R squared dependence, instead of just gluing together the vertex operators, you will also allow these cubic vertices. Okay, so that's now how to relate these cubic vertices with this interaction term, that I don't have any ideas at the moment. But if you could do that, then I think you would really understand how to try to derive the Maldacena conjecture from at least its small radius. Okay, so I guess. So this would be perturbation theory. So the idea is that for every time you introduce a cubic vertex, you introduce a factor of the 't Hooft coupling. Okay, so that's what I wanted to say.
Can you see I was wondering if you can see the incident effects more explicitly by performing the Hori-Vafa duality.
Remind me what that duality is?
So you kind of integrate in and integrate out some fields, and you go to this kind of abelian dual description where you replace the chiral superfields with the twisted chiral superfields, and then there's sort of non-perturbatively generated superpotential, and you're supposed to capture these vortex effects by this effective superpotential, some kind of exponential term.
So that turns an A model into a B model? Is that?
I guess so. I mean, usually we don't, in the gauge index, I mean, it's still kind of sort of gauge linear sigma-like description. Because but it's essentially yes. I mean, it's supposed to produce. I mean, if you go to the usually in kind of RG flow kind of description, if you go to infrared, you're supposed to get the mirror model, but it's more general than the usual nonlinear sigma model mirror duality. Because in that description, usually kind of you sort of have an understanding of the full non-perturbative effective superpotential, and these vortex effects are manifest in that description.
Okay, so this term goes away? Is that when you do this?
No.
It becomes some superpotential term?
No, I think you keep the vector superfield untouched. You just you kind of trade the you trade the phi with something else. So you trade the let's say the chiral superfield phi with the twisted chiral superfield.
Okay. Okay, so I haven't thought about it, but yeah, that might simplify things. I haven't thought about it.
You mentioned that the R equals 0 is Fleischmann.
Yes, so this is,
R equals 0 is
so so when r is non-zero, then instead of being 0, this is going to be something like r squared, which means you can gauge fix. So this is, of course, no longer a solution.
Does it mean that the R equals 0 limit is singular?
Maybe, I don't know. So, of course, it might be that, the hope is that you can start with r equals 0 and deform to get r non-zero. Of course, if r is singular, maybe that's not possible, but so.
But the equation is that R is somehow proxy for Topf coupling.
Yeah. So actually there's some, I mean, when I show this to Cormoran, he says, no, r equals 0 should be singular. Should be non-perturbative effects that make this thing singular. I honestly, I don't have intuition. I don't have enough intuition to answer your question, but the hope is that r equals 0 is just a point that you can expand around.
I mean, in the usual graph gauge linear sigma, like r equals 0 is like the conical point. So
Is that good or bad? So, but can you expand around that point or not?
well, if you're careful enough, perhaps.
Okay. Yeah, so that's my hope, is that you can describe the r small by expanding around this. But I guess if you can't, then probably there's no point in trying to understand the free case. But
So you know local description of these states in these vertex operators, or
do I know what?
a local description? I mean, the local vertex operators are hard to track, or where you trade for the boundary states.
So I guess the honest answer is I don't know the rules for writing down the vertex operator. So you need a vertex operator which somehow made the U1, forced the U1 flux to be non-zero here. So I don't know how to, there should be some worldsheet operator which does this, but I don't know the right language.
But I mean, from this action, you can try to guess what are the physical state vertex operators. Is it very hard, or?
So this action has this U1 gauge field. So after turning on the U1 flux, then you can, the vertex operators are just functions of these instanton solutions. So I think that's, what I said here I think is essentially the vertex operator you want, but that probably doesn't satisfy you.
But if it works, it's not. That I just was wondering what are the.
So it's going to be some, I think it's, in some sense, it's the same thing that Gopal and Gabriel did. It's just constructed, the vertex operator is constructed out of modes of these phis. which you can rewrite in terms of this if you want. So essentially, these modes, you just do Fourier decomposition. So you just write phi near the vertex operator, something like phi n e to the I n sigma. And then this would be at sigma equals 0, sigma equals pi over 3, whatever. So you can relate these two. But this is kind of like some light cone. I mean, I don't know how to call this BRST invariant, but I'm sure there must be some language in which it is.
So in the original pure spinor worksheet theory, do you understand what is the space of states on which you are supposed to take the BRST cohomology? Namely, in particular, what kind of function lambda bar are supposed to be?
Okay, so yeah, so in the original, okay, so if we go back, okay, so first the half BPS, so you can, so this operator here describes all the supergravity states. So that's actually in any supergravity background, not just in ADS5 times S5. If you want to get the massive states, then you have to allow this to also depend on derivatives of x and also derivatives of lambda, et cetera. So this, at least in the flat case and in general, should be work for any supergravity background, should describe the full set of states.
So you say you don't need to think about the inverse of lambda.
No. So you only need to think about inverse of lambda if you want to construct states which are like the B ghost, which doesn't have ghost number 1, 1. But the physical sector is essentially all described by this. So there might be some zero mode stuff that is missing, like the dilaton stuff. But at least a generic momentum, I would think that all states can be described like this, in this way.
Is this a bit like the restriction to picture number in the SR formalism? Because I'm just thinking in example, it's like say in an SR formalism, you have the gamma of negative weight, but you don't have that in the picture number -1, so you don't have to worry about having arbitrary negative weight states. Is this similar to that?
So we don't, one difference is that so for tree amplitude, you certainly don't need any other, what you would call pictures. So this is enough. And in fact, something I didn't mention is that so for open strings, of course, this is the full open superstring field theory, restricting to these states. You don't have to, no. It's true, when you do multi-loop or when you do off-shell states, somehow you do need this 1 over lambda bar stuff. So in some sense, that might be one way to say it, that you need to include 1 over lambda bar dependence if you want to describe what you call different pictures. Yeah, but that's something, well, okay, that, by minimal, it means that there is no lambda bar, so that's a little bit different language. So if you want to construct vertex, there's another thing you can say, which is things like Siegel gauge. So if you want to construct vertex up in Siegel gauge, you also need 1 over lambda bars. So it's related somehow to gauge fixing, which is slightly different from picture, but maybe there's some way to relate them. I guess one could ask in ADS5 times S5, does picture for you have any different meaning, or is it just the same like in flat background? Do you understand my question?
Sorry?
So picture, I know how to define the flat background, like Friedan, Martin, Ekashenko.
There's no worksheet there's no worksheet theory in SR formalism, so I'm not sure there's a sense that you can speak of
Well,
I would also say that in the usual NSR formalism,
no, but sorry, I can say something. So suppose you have infinitesimal flux. Then the point is the Ramond vertex object you insert have to have some picture, right? Because they have to have. So somehow the picture has to get mixed up once you do Ramond flux.
in some vague sense, yeah.
Well, I think that's probably one of the obstacles to doing it, right, in RNS, is that,
Yeah, but I would say that sort of let's say in the string field theory approach, which is a bit more rigorous, we don't, in the string field theory, we don't ever speak of other pictures because we don't take the OPEs of just the vertex operators of the string fields. We replace that with the string bracket, which always adjusts the picture to the canonical one, namely -1 NS and -1 half in R, so you can avoid ever talking about other pictures.
okay, but you have these extra states like the sen?
Well, I mean, you have to include all the offshot states, but
No, but you know, the free, in order to describe, for example, the phi form, I mean, you need to have these extra Ramond states, right?
you're referring to auxiliary?
So in order to describe the open string field theory, and probably closed string field theory also, you have to add this extra sector which decouples, right?
Oh, right. So you're true. That extra sector has this picture number -3/2, but that's not it's kind of auxiliary field. So
Okay, but that doesn't cause problems in ADS. I don't know, I never thought about it, but it's something that you can do in any background?
No, but in that approach, you don't deform the background. So you don't.
Okay, so you're always thinking flat.
I have another question. Have you ever thought about doing this in momentum space? Like in flat space, you would want to match, let's say, to scattering amplitudes, which are usually defined in momentum space.
So I guess the question for you is there some, I would like to do it, but is there some nice way to do it in momentum space with keeping the PSU to 2.4? Do you know how to do it?
I don't think so, because you cannot define momentum in ADS basically.
Okay,
But in the flat space limit, that's what you should recover somehow. But
I agree. Yeah, I guess that's a little bit frustrating that, so as you know, I mean, just computing tree amplitudes in ADS 5 times S5, even the simplest ones, we don't know yet, know the right rules, and I think it's related to that. Okay, so I guess we can stop for 5 minutes and then start the next one.
so here in 5 minutes, right?
Yeah.
You were, yeah, I think I misunderstood before. Your phases are still the local operator, right?
Yeah.
Yeah, I thought because there is this graph duality, but where we really change. So maybe I look at.
So but this is the graph duality. So the faces are the
Right.
vertices again.
Right. So this is, let's say, the original graph.
Yeah.
This was the original local operator, and yeah, now you are doing it like
Yeah.
this, right?
Yeah.
And you're doing these phases.
Yeah.
But yeah, so yeah, it has changed from a point to a phase.
Yeah.
But you are still describing the local operator just now as a kind of Wilson loop, I guess.
So it is the dual. So it's the
Yeah.
so it's F type,
Right. But
not the D type.
because the thing is that in this, let's say, work with Shota, what we really do is we really change by now describing these vertices. So let's say.
Sorry. So this was.
So this is the original vertex this is the trace of set.
Okay. Yeah.
You're changing this point now by this phase,
Yeah.
but you're still describing the trace. cube that you draw is like really describing the vertices of the cube instead of the face.
So for you, but when you say, but this is also in the Chern Simons thing? I mean, in the thing you did with subtotally.
Yeah. I mean, we start from that formulation, but when we say that we do this open duality.
So the open duality should have both, and that's essentially the open duality, right? It's the one that relates this to this.
Right. But we always in both cases we always have vertices. Like.
So I thought the open duality was precisely that you change your vertices change to faces and vice versa.
That's correct, but the thing is that in both formulations, I mean, let me say, in both points of view you have faces and vertices.
Yes.
It's just that they get exchanged
Yeah.
in the description.
Yeah.
But in your case, you are going from one description where you have vertices, you go to the other, but on the other, you still choose to describe the faces, which correspond to the original vertices.
So the Engels-Feynman diagrams,
Yes.
the vertices of the Engels-Feynman diagrams, for me become faces in
Right.
the Riemann surface, and
Right.
vice versa.
Right. So this is the original Supreme Mill.
Yeah.
And you start with these vertices,
Yeah.
and then you're describing the F prime, which is exactly the original
Yeah.
vertex.
Yeah.
But when we do this raw model with Shota, we actually choose the vertices.
And that's
prime.
why you get this duality.
Yes.
Okay.
So I was wondering if you can also. I mean,
No,
that was
no,
the
no,
question
I understand. Now I understand.
That Alberto was asking.
So if there's another way to describe it in which, so there was a paper I wrote maybe 4 or 5 years ago in which I was getting something more like this. So you start with, trying to remember it. So the propagators, in this case, you want the propagators to be actually the string propagators. So for example, the thing that I call superdeterminant, this should come from it should be like the zero, alpha prime going to zero limit of the string. So let's see. So the open string, so you either think of this as being the edges of the open string, or you think this as being the edges of the open string.
Right.
And that's related to this duality.
Yes. I mean, the propagator has to be the same actually, but it's just that you're trading the description. I mean, in this cube, do you draw the edges are always the edges, right?
Yeah.
It's just whether you're saying that you're doing the faces or you are sending.
Well, so for me, the propagator is actually from here to here.
Right.
Yes. In other cases, we
yes,
from here to
yes,
here.
but still you're describing the same edge of the cube. Yes, I was wondering if you can find.
So at the moment, I don't know how, but there's some clues that there might be a different way to do it.
Right. So that would be, I mean, this raw model.
So when was this?
Well, I mean, this is also written by Rajesh for the theory. But also Shota has a paper where he does it for these giant gravitons.
Okay, so Shota by himself? Or
Shota with 2 more goals. I can send you the paper.
Okay.
But it's also in my paper.
Okay,
So
your last one.
Yeah, with Simon.
Okay. Yeah, Shota was with one with Rajesh recently, right?
Yeah, they also wrote another paper. So yeah, this is being used already
Okay.
many once. Yeah.
Thanks, man.
Do I need to put this on?
Sorry?
Do I
Yes.
need to put this on?
It's already on. Yeah, I tried to get this in there. Okay, so
All right, thanks. Thanks for the workshop and for asking me to speak. I'll say a few things about something I've been working on in the last couple of months with a student undergrad from Tsinghua who's coming to Davis as a grad student, Jianming Zheng. And there's some related work by these folks, Beatrix Mollman, Vladimir Volansky, and Yanis Yaris, and some ongoing work with Beatrix and Jianming and Yanis. So I'm not sure how many people are familiar with the Virasoro minimal string, so I'm going to review some aspects of it for the first 10 minutes or so, and then talk about the thing we did with the supersymmetric extension. The broad goal, at least the way I came to it, was to try to understand some minimal string constructions with simple ingredients, namely Liouville theories or variants thereof. And the part of the idea was to realize the old story which we've learned very well in the early 90s and then later in the early 2000s, and more recently, thanks to work by G and friends, that the minimal string constructions, the non-critical strings, are a very good playground for understanding non-perturbative effects. And one of the constructions I'm going to show you is going to be a theory where there don't seem to be nothing interesting in perturbation theory, which is hard to prove, but seems to be true. So all the effects that you would like to study in a theory are purely non-perturbative. Okay. And the motivation here came from thinking about this, what I will call the VMS, the Virasoro minimal string, which was studied by Collier, Eberhard, Mollman, and Rodriguez in a series of papers a couple of years ago. And they have some variants, which they call the complex Liouville string, which I won't talk about. And this was coupling C greater than 25 Liouville theory with C less than 1 Liouville plus world sheet gravity, namely BC cos. And for historical reasons, I will call this the space-like theory and this time-like theory. So this is a critical string with these just simple matter ingredients. And what they showed was that this theory has connections to a bunch of things. So the connections here are to a matrix model, which I will review in a second, some double scale matrix model with a spectral curve, which I'll write down. It's also connected to intersection theory or moduli space of Riemann surfaces. And to chiral 3D gravity. And much of this was developed in the paper by the people I mentioned 2 years ago. And our motivation was to try to ask what happens if you take these ingredients and supersymmetrize them by studying coupling n equals 1 Liouville to n equals 1 supergravity. And there's some answers that I'll tell you, and there's some open questions which I'll outline towards the end of the talk. So let me first review this theory just to orient ourselves what there is. So let's start with the ingredient space like Liouville. So this is a non-compact CFT in 2 dimensions with parameterized by a parameter B, and the central charge is written in terms of B. And the theory has a very simple spectrum. It has a continuous spectrum with vertex operators Vp, whose dimension is set by P and this parameter B, and I'll take P to be in plus. What's remarkable of this theory is that given this not only the spectrum known, but the theory can be bootstrapped, and the 3-point function of this theory is known thanks to the famous DOCZ formula. It's some function of these momenta. Let me just call it C, P1, P2, P3, whose details will not be important for what I'm going to say in the rest of the talk, but the formula is explicitly known in terms of some special functions, Barnes double gamma functions. We won't need those details for what I'm about to say. But and if B is real, and I'll take B to be in 0, 1. If B is in that range, you can see that central charge here is bigger than 25, and that defines this regime of the theory. Given this data, you can just bootstrap any higher point correlator. So you can just compute them using the conformal blocks, and this has been done in many examples. So the theory, as far as the conformal field theory is concerned, is completely under control. What I will do when I write, what I will introduce here is the normalization of these vertex operators slightly differently from what's usually done in the literature, and argue that that's useful. Let me call this rho bosonic P1. Where this rho bosonic is the universal Cardy density of states. Let me just ignore factors. Okay, so it's slightly unconventionally normalized compared to the usual. So this is coming because of the reflection amplitude. So if I just take P in the reals, then I only have the first piece. But the second piece, if I take P in R mine, in the case where there's reflection of the Liouville wall, I will get that piece.
So usually in the natural convention where you write the asymptotic wave function to be kind of analytic in B, you would end up with a non-trivial reflection phase.
Yes. Yes. But you're right that if I keep P in R plus, then I don't see the second term. So in the external states, I'm just going to keep P in R plus. Okay, and with this data you can, and I write this because this is going to be important for the later discussion with the matrix model. Now let me introduce the second player in the time-like Liouville theory. And that I'm going to, since I'm having to write on the board, I will use hats. And it's still parameterized by one parameter called B hat. And the definition of the parameters of the central charge is in terms of this B hat as such. And now there are again vertex operators with real momenta, and the holomorphic dimensions are switched. Okay. One can again bootstrap this theory, and this was done also by Zamolodchikov and then by Kostov and Petkova in the early 2000s, but checked numerically later by Ribot and Santa Chiara. And let me make it clear that this 3-point coefficient is a function of B and of the 3 momenta. And the time-like 3-point function is given to be the space-like 3-point function inverse with momenta replaced by I times momenta and the structure constant inverted. So that's the building blocks. So now we can try to compute.
Could you remind me, so in order to satisfy crossing,
Yeah.
the spectrum of the primaries needs to be along which contour?
Yeah, so to satisfy crossing, the contour of integration in the P space is slightly off the real line because this guy has poles everywhere along the real
And
line.
that's P hat or P?
P hat. So this is the proposal, which, as far as I know, was never derived, but it's a thing that was checked to satisfy crossing.
And if I take the limit C hat goes to 1, what does this theory become?
If you take the limit C hat goes to 1, I think it is different from the Runkel-Watts theory, which is the limit which you get, that's the limit you get as you come from the minimal model side. My understanding is that in a complex C plane, you have this ray running between -infinity and 1, and you have the natural ray defined between 25 and above, and you can analytically continue from here anywhere onto the complex plane to define the complex Liouville theory, and if you sort of land on the rational values that define the minimal models, that agrees by going off the complex plane. But along this ray, there's a new theory which is defined by these guys.
Now, when we call this kind of like Liouville theory, is there actual concrete understanding of the statement that this thing actually comes from the path integral based on the time-like Liouville action?
I don't think so. I don't think so. And I think that's there's been some recent work which I haven't followed by this mathematician, Saurav Chatterjee, of trying to interpret this time-like structure constants in terms of some probability theory, but I haven't sort of.
But even that large central charge, can't, there's no semi-constant charge.
Large negative central charge.
Large negative.
I don't think so, but I could be wrong about this.
Can you say in words what CB is, how it depends on B? Is it secret?
Not really. I can tell you what the thing is. So CB depends on one function. It's built out of one basic function, which is this Barnes gamma function.
Yeah, I guess I want to know what the subscript B means.
Yeah. So this Barnes gamma function has this. Someone can help me with this.
Okay, thanks.
Something of this kind.
Okay, more complicated.
Yeah, it's a bit more complicated than you think. Yeah. So it satisfies the it satisfies some shift relations with when you shift by b and by 1 over b, and that's what is used to obtain this.
There was this old paper by Harlow, Maltz, and Witten on the time I video. Is that related to this at all?
So the way they were trying to define that, as far as I remember, was by doing analytic continuation, and it is related to this. But I just want to emphasize that this is not obtained by simply analytically continuing the space-like structure constants because of this inversion and because of the contour of integration. Okay, so there's some theory for which you can find details in the literature, and you can put these together. And now, if you put them together with the BC goes, we can define a critical string theory, which is what these people did. And the physical vertex, so if you want total central charge C space-like plus C time-like plus CBC equals 0, this implies that the theory is defined with B equals B hat. And the physical BRST vertex operators in this theory are simple. Are just space-like vertex operator times time-like vertex operator with P and P hat related by this analytic continuation. Okay. A consequence of this, so first consequence is that the 3-point function, so let's call this script P, is that this 3-point function is a pure number on the worldsheet. So let's say I normalize to 1 by convention. Second, so there's a second statement which
Sorry, the one, just to be sure, the one is not by convention, it's because of cancellation of these two. Right?
it's because of the cancellation of these two, but I've chosen the normalization in both cases of the vertex operator, so the cancellation happens. There's also some normalization I could have put here, which I've chosen in the vertex in the string vertex operator itself. Let's say what the sphere amplitude is. Good. Now, one can then compute higher point amplitudes for this theory. And there's a claim which I will state, it has not been proven but been checked, that this guy computes the volumes of moduli spaces of Riemann surfaces with n geodesic boundaries, and the geodesic boundary lengths are pi. Okay? Of course, one can do the worldsheet calculation by doing a conformal block decomposition of this endpoint function using the structure constants and doing the integral of the worldsheet moduli. This has been done in some small number of examples numerically. The volumes of these moduli spaces can be computed by a matrix model whose spectral curve is this guy.
The B depends? When you say volume of sigma g?
Yes, sorry, so maybe I should have said for experts, let me call them deformed volumes, where the volumes are deformed by B. And just to say what Henry was alluding to, the volumes of these moduli, of these Riemann surface moduli spaces is computed by the matrix model due to JT gravity, the Schatz-Schenker-Stanford matrix model. This gives you a one parameter deformation of that matrix model, and that parameter is B, because if you take the spectral curve and take B to 0, you get back the spectral curve of the JT gravity matrix model. So B to 0 limit but it also gives JT gravity on the world sheet. Okay. So when you put together the space-like and time-like theories, if you write them in terms of the Liouville action, by a field redefinition you can show that in the limit B to 0, what you get on the world sheet in conformal gauge is just JT gravity. So in some sense there is some nice connection between JT gravity, a deformation of JT gravity, and a world sheet string theory, where the deformation is characterized by one parameter, namely B. Okay? I won't say anything about the other two connections in the talk, because these are not been developed in the context of superstring. What I want to say is that given the spectral curve and the matrix model, you can do topological recursion and work out what these deformed volumes are, which is how these folks worked out what the volumes were. These volumes are very simple functions of these momenta, which is not at all visible from the structure constants here. So although for 3-point functions the structure constants simply cancel and you get pure number, for higher point functions you have to compute the correlators of the space-like and time-like theories separately and then stitch them together from the world sheet. And that doesn't immediately imply that you get simple functions of the momentum. Okay. Nevertheless, what was checked was for 4-point sphere and 1-point torus amplitudes, that you can numerically do the integrals of the world sheet moduli and check that the answers you get are consistent numerically with the answers you would predict from the matrix model. Okay? So I emphasize this because there's something non-trivial which I think is going on here, which I will come back to when I talk about the superstring. Good. So that's all I want to say about the Virasoro minimal string, and these are the only building blocks I will need. So let me just ask for now if there are questions about this construction before I move on to the superstring case.
Is there any sense in which if the C hat goes to one limit, you can view this as some kind of time-dependent background sequence one string theory?
Probably, I don't know for sure. Already it's not clear to me what the meaning of this theory is from a space-time point of view because of the time-like Liouville. As you probably know, there's a nice paper by Victor trying to interpret this as some kind of string cosmology, and he was actually trying to study it in the C hat equals 1 limit. But there it sounds, the picture that I would draw in target space is if I draw this to be the time-like Liouville direction, let's call it psi, and this to be the space-like Liouville direction, and let's say, so this is the strong coupling region of the space-like Liouville, and I cut off the time-like Liouville in the past. So it looks like I have some kind of Big Bang and some free states out here, but it's not clear that these free states out here can be mapped to the C equals 1 case. So this is a question that I have, but I don't have an answer to.
This could be clarified if you know what the action is.
But it's not, as I said earlier, it's not clear to me that even if I knew what the action was, whether this theory is defined, this is related to a path integral question, whether this is obtained from that action by some path integral quantization.
No, that's what I meant.
Yeah,
When I
yeah,
said the
yeah,
action, I
yeah.
meant if
Yes, agree. I agree with that. Yeah. Yes, Edward.
The question for the department wasn't again only receives contribution from the boundary of the moduli spaces. You can think about it that way.
You can think, I mean, the topological recursion is done in the standard way. It only takes as input the spectral curve.
Right. But actually, can you think about the topological recursion like in topological string where it only receives contributions when when you have differences on the worksheet, the worksheet boundary analysis fixes.
I think that's roughly speaking true. It was not shown from the worldsheet.
Yeah, that's what was
Yes. The reason something like that must be true is something I could say is that even though these functions are complicated, when you look at the correlators, the worldsheet integrands are well behaved, and the worldsheet integrals, I mean, in fact, they were actually convergent, so they could just do the integrals numerically in the simple cases. So, but the recursion was derived using matrix model technology, not using worldsheet technology. Okay, so that was important, and you'll see why in a second. All right? People happy? Okay, so let me make this supersymmetric and then tell you what we did. So the supersymmetric theory would be to couple n equals 1, 1 Liouville theory with central charge C greater than 27/2 with a theory with C less than 3/2 plus the worldsheet superconformal goes for n equals 1, 1 supergravity. Okay, so that's the theory we want to study. This theory was bootstrapped back in the 90s. I'll review that in a second. And one of the main things both papers did was to bootstrap this theory, at least present structure constants for this. So I'll start with the space-like theory because there's a bit more data to give, and then tell you what happens in the time-like theory. Some things some of you might be able to guess, and then we'll see what is implied by them for the worldsheet construction.
Just to be sure, you are considering type 0 GSO projection.
I'm going to come to the string, but yes, indeed it will only be type 0 GSO projection because there's no chiral GSO projection for this set. Very good. So let's start with a space-like super Liouville theory. So now the main piece of data I need to tell you is what are the vertex operators, and what the parameterization is. So my parameterization is still Q is B plus 1 over B, but now the central charge is 3/2 plus 3Q squared. The main novelty here is now we have to talk about different sectors because this theory has a Liouville field and its fermion partners. So I need to tell you what the vertex operators are in the NS and Ramond sectors. So in the NS sector, there is a superconformal primary. There is its descendant, which is spin half, and then there is a scalar, which is a double descendant. So that's the multiplet in the NS sector. And in the Ramond sector, there are two operators, two degenerate operators, which I will grade by their worldsheet fermion number. And this is the total worldsheet fermion number. As you said, there's no chiral left and right moving fermion number for this theory. So I'll call them R plus R minus. VP has conformal dimension HP, which is P squared over 2 plus Q squared over 8. And then these get half added to them, and this guy has conformal dimension HP plus 1/16. Now, even though the many operators. You might ask, what are the basic building blocks? What are the essential 3-point functions I need to give you to bootstrap the theory? And there turn out to be 4. Everybody else is fixed by superconformal word identities. And let me give these some names. They're also built out of the same Barnes gamma functions. Now they're slightly modified because you have half shifts because of the Ramond sectors, but you can use the same building blocks to write them. Okay? I'm not going to write the formulas. This is something that you can find either in our papers or in the earlier literature of what these formulas are. Okay. So there are again functions of these three momenta. And momenta I'm going to still take in to be in the positive half line.
Could you W and V?
So V is a superconformal primary. W is its descendant in the with respect to G half and G minus half. G half and G tilde minus half. So think of it as a single superconformal multiplet, n equals 1, 1 multiplet. So this is the bottom of the multiplet, top of the multiplet, that's the bottom. Okay, and 3-point functions of VV lambda are 0 by spin, but VVW 3-point functions are not 0. And the important thing is that they are not fixed by superconformal word identity. Okay, so in the NS cycle, you need 2 independent structure constants to define the theory, not 1. Okay, good. So how much time do I have? So keeping time. 11:30. Perfect. All right. So let me say how this was done in the 90s. This was worked out by, and I like with the Liouville theory, how the structure constants are found. Just in words, so that people are aware that this is not some black magic where someone just wrote down some structure constants and checked that they work. So there's a nice trick which goes back to Teschner. The idea is to use the fact that you write down some null state decoupling equation for the Virasoro primaries, and Virasoro primaries with momenta are null states in both the bosonic and the supersymmetric theory. In the supersymmetric theory, when R plus S is odd, they are Ramond sector states, and when R plus S is even, they are NS sector states. Okay. So you write down a 4-point function with one degenerate operator and use that to derive a functional relation between structure constants. That functional relation relates things like so you get functional relations for these ratios. So this ratio turns out to be proportional to some ratio of gamma functions, and you get similar relations for swapping of signs. Sorry, the other way. And for B replaced by 1 over B. Okay, so you have 4 relations, and then you can ask what functions satisfy these functional relations. And having figured out that function, you can just write down the structure constants. Post facto, you can check that the structure constants satisfy crossing, and therefore you have a well-defined CFT.
So this is very similar to the computation of Teschner.
Exactly the computation of Teschner for Liouville theory. The same thing works in the super Liouville case. In fact, this is what these folks, Rashkov and someone else, Shashnikov and Pogosyan did very soon after DOZZ and Teschner in the maybe mid-90s. I should also say that some aspects of this, including numerics, were checked by Xi and Bruno and Victor in their papers when they were looking at C equals 1 superstrings, minimal superstrings.
So I always thought the Teschner's trick, and it is implied to this case,
Yeah.
is an extra assumption on its own, because it's not obvious when you continue that the null state has to be the 0 state.
That is true.
And in fact, I think this trick will fail if you apply to n equals 2 Liouville.
Correct. I agree. Yes. I mean, which is why n equals 2 Liouville is still not fully understood for some of these purposes that I want.
Well, as far as I know, n equals 2 Liouville is solved using the TPO-Sigard description
Yes.
from Tosa.
Yes.
But you can, another thing for n equals 4 Liouville is not solved as far as I know.
Okay, so we have this piece of data. Now, I can say the same thing about the time-like Liouville theory, and my parameterization is going to be as before with some b hats. So where did it go? So now I'll take q hat to be b hat minus 1 over b hat. So the other way around. And the central charge is 3 halves minus 3q hat squared. Okay. And again, there are hatted versions of all these vertex operators. And so I expect hatted versions of 4 structure constants. Let me call this C plus and this C minus. Okay. Right. And the question is to determine these guys. And what I didn't tell you when I talked about the bosonic theory is when you look at the structure constants for the time-like Liouville theory, one way to obtain them is to use these shift relations of Teschner. And realize, and this is what Zamolodchikov did, is to realize that there are 2 solutions to the shift relations. One which defines the space-like theory, and one which technically defines the time-like theory. The formula I wrote down that C time-like is 1 over C space-like came by a second solution to the shift relations. Okay? So now we could sort of apply the same trick here to find the second solution to the shift relations for the super Liouville theory. Okay. So I get to pose questions, so let me pose questions. What do you think is the, so I'll give you half the answer. Half the answer is there's some inversion relation. But what do you think is the inversion relation between those 4 structure constants and these 4 structure constants? They form a matrix, but not. But, well, first of all, they can't. These guys can't talk to these guys. NS and R sectors are separate, so the inversion has to happen between these 2 and between these 2. But something interesting happens, and I will let you guys ponder for 2 minutes why this happens. Okay, I'm going to write this kind of formula, but let me explain this. Let me extend my notation.
Because you're on 3-point amplitude that you want.
Okay, very good. I do want it, but you'll see that it's not. It means that the shift relation know about something else that you've already guessed. Okay. So that's the inversion relation we get. And my notation basically again means that this theory is parameterized by b hat. So it's the C with b hat, and the p is replaced by I. P hat's replaced by IP. In these formulas on the right hand side. Okay? And for sanity, we just took the numerical code that G and friends had used to check crossing for the space-like super Liouville theory, and we checked that the crossing symmetry is respected for this case. Okay, so we are sort of confident that these are the right structure constants that is defined in well-defined CFT. So now let's put everything together and define the super Virasoro minimal string. I've chosen the parameterization such that, again, the critical dimension, 0 total central charge on the worldsheet requires that B equals B hat. And the time-like momenta are related to the space-like momenta by this factor of I. Okay. So let's look at first NS vertex operators, which are universal, and then we'll come back and talk about GSO projection and talk about the Raman vertex operators, which care about what I do with the GSO projection. Okay. So in both theories, there is one superconformal primary. So in the NS sector, there's an obvious, in -1 picture, there's one obvious vertex operator, which is VP V hat IP, dressed with ghosts. Okay, so e to the minus phi tilde, CC tilde, blah, blah. Okay, and we will need the vertex operators in the 0 picture, and which I'll write down in a second. But before that, I want to say something about how we are putting together these two theories. So let's ask what the worldsheet's currents are for the matter sector. The usual choice, the conventional one, is to say you just add up. So G is the supercurrent in the n equals 1 theory. You just add up the left and right moving supercurrents for the space-like and time-like theories, and that defines the matter supercurrent that you couple to n equals 1 supergravity. But you could do something else, and I'll define that with a prime. And for some reason, I've never seen this done in the minimal string discussion, which confuses me, but someone can tell me whether they have seen this. We can put a relative sign on one side. Okay. This issue does not arise for the C equals 1 non-critical string because there's additional symmetry there. But for the minimal string, usual discussion, if you go back to the early 2000s, only discusses this choice of supercurrents. And I'm ignoring here cocycle factors which are necessary. Okay. There's a difference for the two because you realize that W is a descendant of V under superconformal generators. So if I write the NS vertex operators in the 0 picture, it's basically going to be acting with the matter superconformal generators minus half, graded minus half, and G tilde minus half on this guy. So it's going to have a piece which is going to be like VW let me just say plus 1. Okay, and this sign Maybe the sign is here. Is that sign?
Did you say that in the minimal string case it doesn't matter, the sign?
I think the sign matters. It's never been discussed as far as I understood from the literature. Okay.
It's not just, there is no Z2 symmetry of the minimal model that just say that.
This I'm not sure about. So this is the part I'm not sure about. This theory definitely does not have a Z2 symmetry, so these two signs are independent.
There are two different models.
So there are two different models here, yes, but in fact, in a moment I'm going to tell you the four models. Okay. So this sign is going to be important in 2 seconds. Second, and
So just to be sure, I mean, of course, if that sector were just a free boson and free fermion,
yes,
you can just flip the sign of the fermion.
exactly. But nothing is free boson or free fermion here, so I can't flip signs, obviously. Yeah, indeed, agreed. So that's why I said that there's a difference between the minimal models, what are called minimal superstrings, coupled with the C equals 1 and versus the C equals 1, because there in the C equals 1 there's more structure. And in fact, I was misled for a long time by the C equals 1 analogy until I realized that the fermions are not decoupled. Then G also asked earlier what GSO projection I make, and let me define the worldsheet fermion number to be the fermion number for the space-like theory, time-like theory, and the fermion number for the gauss. And I have two choices. As usual, for the diagonal GSO projection. So the usual convention with the +1 gives me the type 0 theory, and the -1 gives me the type 0A theory, 0B theory, and the -1 gives me the type 0A theory. And I have in addition another pair of Z2 choices here. So I have 4 theories I can write down, so you can call them A, B, A prime, B prime, as you wish. Okay. Okay. And now, depending on what I do, how I've imposed the GSO projection, I can tell you what the Ramond vertex operators are. Okay. So 2 of these theories. So let's give these guys the conventional names. So with this choice of the worldsheet supercurrent and -1 to the f worldsheet equals +1, I'll call it 0b, and -1 I'll call 0a, and here I'll call 0a prime the theory with +1 and 0b prime the theory with -1. Some convention choice. Okay. 2 of these theories have no Ramond vertex operators. Okay, and by convention I've chosen one of them to be 0a, the other to be 0b prime. So this is very familiar from the minimal C equals 1 case, where the type 0 C equals 1 theory does not have Ramond vertex operators, it has Ramond fluxes. In the other 2 theories have, in the -half picture, they have Ramond vertex operators, which are like r plus r minus hat plus r minus r plus hat, and then the p's go along for the ride. And the other guy has r plus hat. Okay, so maybe there's a sign here. All right. So this is our data. So now we can just start computing correlation functions and seeing what we get. So let's compute first the NS sector, which is the simple thing to do. And in the NS sector, you want to compute, so let's call this V minus 1, and let's call this V0, and with a plus sign, and V0 prime with a minus sign. Okay. So I can either compute V minus 1, V0. That's for one of the theories, one pair of theories, because this is an NS sector. And for the other pair of the theories, I should compute V minus 1, V0 prime. And I've implicitly used the PCO to shift the picture number for the NS vertex operator, so that the total picture number for the sphere amplitude is +2. And here I get 1 plus 1, and here I get 1 minus 1. So in one case, the amplitude vanishes. In the other case, the amplitude adds. And something similar happens in the Raman sector. I won't say what the numbers are, but again check because of the relative shifts between evens and odds. One amplitude of Raman of two NS and one Raman operators vanishes. The other one is non-zero. Okay. So now let's go back and ask, what was this model supposed to be dual to, and what was the expectation from that matrix model dual? So in this case we have, it was conjectured, and this is a partial conjecture, that one of the sectors, it wasn't specified which, is dual to a matrix model, and this was in the original paper of Scott and friends, with a spectral curve given by this Koch formula. Okay. That was a conjecture that they put forward. But
For the supercharge or for the Hamiltonian?
I'm coming to it. Okay. So they just said this. So I'm going to explain what Henry just said by taking the B to 0 limit, because then I can explain from the JT gravity side what the expectations are. So let's take B to 0. And this limit, which is just JT supergravity, was analyzed very nicely by Stanford and Witten. And they, of course, talked only of two theories, the 0A and the 0B theory. Okay? And in the JT supergravity, the distinction between 0A and 0B is a question of whether -1 to the f is present or absent in the two theories. Okay? So they both are defined on super Riemann surfaces. In one case, in the 0A case, -1 to the f exists in the spectrum. In the other case, -1 to the f doesn't exist. So in 0B, you get to compute volumes of moduli spaces of super Riemann surfaces with geodesic boundaries, for which you get to prescribe NS or Raman boundary conditions. And you just get to add those volumes up without signs, because there is no -1 to the f. In the 0A case, you get to compute volumes graded by -1 to the f. So you can compute, so JT supergravity. Here the observable is what's called the mod 2 index, namely volumes graded by -1 to the f, whereas here you just compute volumes of supermodular spaces, volumes of moduli spaces of super Riemann surfaces. Okay? And Stanford and Witten did much more than that. In the latter case, they used the matrix model inspired from SYK, supersymmetric SYK, to work out what topological recursion would be. Okay? So they have a topological recursion formula for this case explicitly, and they have a similar statement for here. But now let me tell you what happens in this case first. So let's first look at the simplest example in 0b, namely the ingredient that goes into the topological recursion, the 3-hole sphere. The 3-hole sphere with 3 ns punctures has a supermoduli space which is of dimension 0/1. Okay? Because all the bosonic moduli, it's like a 3-point function on the world sheet, all the bosonic moduli are soaked up, but picture number is not matched, so I have one fermionic modulus to work on. Since this space has one fermionic modulus, this space has 0 volume. If this is a seed for topological recursion, it then follows that every perturbative amplitude in the 0b theory is 0. Okay? And you can likewise convince yourself that if you this cosh deformation of it also, because it's a spectral curve with no edge, also has no perturbative amplitudes from the matrix model side. So there is a prediction from the matrix model, namely that one of these theories has no perturbative amplitudes at all. Secondly, for the 0a theory, this statement is still true on the sphere. In fact, all the genus 0 amplitudes vanish, but higher genus amplitudes don't necessarily vanish because you get to insert a -1 to the f. Okay. They of course didn't talk about the other 2 examples. Okay. So of course, now you see, for one choice, and I may pick my signs inappropriately in the talk, but for this choice, it is true that the ns sector 3-point amplitude is 0, and assuming that there is a duality, you should be able to show that the higher point amplitudes also vanish likewise for this choice. Okay. So that has not been done. So what has been done so far is just computing the simplest 3-point amplitudes. And I'm going to pose so something we're thinking about, and I'm going to pose a question for the audience.
Sorry,
but
just say again, in the dual description, you have a proposal for all 4 different theories, or?
no. So the supergravity description, which is the only thing that's been worked out, had two theories discussed, and we initially, okay, so if you read our paper, we sort of did the following. We didn't talk about 4 theories. We talked about only 2 theories because we only looked at the theories where the supercharges were the sums of the left and right for both the holomorphic and anti-holomorphic sectors. And we realized that when you write down the structure constant by solving Teschner's the shift relations, overall signs are not fixed. Okay. So what we said was there's a sign here, and there's a sign, let's say, here. Okay, which is unfixed and unfixable by consistency conditions with bootstrap. And we asked whether we could use the world sheet to pick out some signs for us. Okay? Of course, you realize that this choice of signs, the fact that C hat W is a sign, can be mimicked by shifting the supercharge from plus to minus because of this relation. So what seems to be the case is that there are 2 obvious examples that you would say are generalizations of 0a and 0b, and 2 new theories which don't seem to have any natural connection with what was discussed so far. Okay. There's a puzzle that I don't know the answer to, namely, what I would have liked is the 0b theory have all amplitudes be 0, because the argument I gave you was for the NS sector, but a similar argument holds for the Ramond sector. And our choice of signs with the GSO projection seems to go opposite for the Ramond sector, and that I'm confused by. So whatever choice I want for here seems to be the opposite sign I want for the Ramond sector. So there's some incompatibility with the NS and R sectors. Okay. there's something more important, which is what we are trying to check, namely, how do the higher point amplitudes actually vanish? Okay? Because unlike the bosonic case where the higher point amplitudes were some simple polynomial functions which you had to compute and check, here the target is very simple. You have to show something is 0. And it's very easy to see why the higher point amplitudes of the sphere are 0, because for NS sector, the moduli space of the holomorphic moduli space is simply this. So any number of NS boundaries will give you 0 because there's always one extra fermionic direction. Okay? It's absolutely invisible from an explicit calculation on the world sheet. So if you think of trying to do a 4-point function on the sphere in the NS sector, you would want to compute something like V minus 1, V minus 1, V0, V0. And now you realize that these fermions that I could ignore for the 3-point function, because there is no 3-point function between 2 bosons and 1 fermion, is no longer true. There are 4-point functions of all kinds. So there's some complicated admixture of things that somehow sums up to 0, which should have a much easier proof given what we know the answer to be. Okay? So the question I have for people who've thought about this is this problem easier to think of shell without actually putting the PCOs on the vertex operators and showing that there's some kind of analog of topological recursion directly from the world sheet that allows you to conclude, given the basic building blocks, that the full amplitudes vanish to all orders in perturbation theory. Okay. And what guarantees that you have a string theory whose perturbative amplitudes are all 0, and this theory has purely non-perturbative effects without the theory not having been constructed with any topological symmetry to begin with. It's not some topologically twisted theory, it's not something trivial of that kind, but nevertheless, it actually has no physical amplitudes. Okay. Or is there something we're missing, and whether this is the duality is much more subtle than what we've conjectured it to be. Okay. So I think I am pretty much on time, so let me stop here and take questions afterwards.
So there was this fact about the sig hat equals 1 times ρp theory, which was always mysterious to me from the working perspective, which is the fact that if you take the plus and minus in the combination of NS and R states, the scattering amplitudes decouple to all other perturbation theory.
Yes.
Is there something analogous to that here?
This statement seems analogous, this vanishing seems analogous to that. And in fact, I was conjecturing that there was some way to derive recursion and there must be some simple way to see this. And Victor told me that there is no simple way for the same reason, that there is no simple way to see why that decoupling happens from the worldsheet side. But I don't know.
Is there a reason why the other lambdas don't get a 3-point?
So there is a 3-point function V lambda, but that's related to this guy by superconformal word identity. So these are the basic building blocks. Everybody else is given to you by some superconformal word identity. What I should have said, and maybe didn't emphasize enough, is you can just try to write down the full set of 3-point functions in the NS sector, and then impose superconformal word identities. You'll find that the solution is determined up to 2 undetermineds, which you have chosen to be these 2. The easy way to just write it in superspace and check that there are 2 undetermineds in superspace. And likewise in the Ramond sector.
This is just a question, I think I missed it. So there are 4 theories.
Yeah.
You know for sure that in the B goes to 0 limit.
Yeah.
2 of those theories don't land on JT Subra, or you conjecture?
2 of them don't seem to land on JT Sugram. And let's look at one of them which gives you the plus, the 2, up to some normalization, non-zero 3-point function. They seem to land on something which sounds like you look at the supermoduli space. There's some volume form on the supermoduli space that you have to integrate to get these volumes. And you flip some torque class by hand when you do that volume computation, and then you get this. So when I first told this to people who were sort of thinking about the Virasoro minimal string, because they have this connection to the chiral 3D gravity, they wanted some connection here to counting superconformal blocks. And it was a bit surprising to them that you get 0 because there should be some count of superconformal blocks. Okay? And it sounds like to get the count of superconformal blocks, you do some violence to the measure on moduli space integral to get this to work. But I haven't worked it out in detail myself, so I don't know whether this is true.
So even if could there be non-trivial debrane states even for the?
Yes, there are, and I didn't talk about the debrane states at all. So like in the JT limit, you might want to attach trumpets to them and compute, the wave functions and so on, for both the trumpet and for the disk and for the double trumpet. And for the VMS, these are all worked out with some assumptions about what the debrane states are in the time-lag theory. If you make some simple minor assumptions of that kind, some things seem to work out for us, but we weren't able to justify why those are the right things. And I haven't gone back to check what happens with our sign flip choices.
So there was this non-trivial choice of contour.
Yeah.
And we will.
Mm-hmm.
Wondering if the same prescription of the contour is supposed to still work for loop amplitudes? Or torus correlator, let's just say torus correlator.
It was supposed to work for the torus correlator as well, yes. And
that something has been checked, or is there some expectation?
What was checked was in their paper, they checked the 1-point function of the torus.
But even for the time lag?
Even, yeah, to get the 1-point function of the torus explicitly for the Virasoro minimal string, they needed time lag case as well, and they used that piece of data. So yes, so there's some evidence that it's the right prescription, but I agree with you that it's not. It's something that just came out of a check. It's not something that's been derived, and the same thing seems to work in the supersymmetric case. Again, we didn't derive it; we just assumed and checked that it works.
At large negative central charge, is there any reason why we can't just check whether it agrees with the semi-classical?
Well, one issue I thought was that this action is unbounded from below.
But are there still saddle points, et cetera?
Yeah, so do you trust the saddle point evaluation when the action is unbounded from below? I think some people are thinking about this, but there were some attempts. So there's a paper of Dio, Beatrix, and someone else who tried to make sense of it, and they were unsatisfied with their result in saddle point. But yes, I think that's a good question. If that would sort of partly justify some statements.
Okay, so let's thank